All right, perfect. So thanks everyone for joining us today, both in person and online. Today we have the pleasure to host Changjian, who is a postdoc here at Mila and at McGill. And he'll share with us some thoughts on algorithmic fairness in the context of medical imaging. So before handing the mic over to you, Changjian, let me remind you all of some house rules. As usual, clarification questions will be allowed to be asked during the talk. For people in person, you just have to raise your hand. I'll give you the mic and you'll be able to ask your question directly in the mic so that people online can hear you. And for people online, you just have to type chat question or I have a question in the chat. And when the time is right, I'll let you directly ask it. Of course, there'll also be some time at the end of the talk for people to ask further question, make some comments, or have a more informal discussion with Changjian today. That's pretty much it for me. So whenever you're ready, Changjian, the floor is yours.
Okay. So hello, everyone. I'm Changjian. So before starting my presentation, I just a very short brief introduction about myself. As Rim said, I'm currently a postdoc fellow on the TAL Arbor. And previously, I got my PhD in Navarre last year working on the distribution shift problem. And during my postdoc, I'm working about 1 year in the bias and the fairness issue in medical domain. So today, I really would like to share some discoveries and our thoughts in the bias and the fairness issue in medical imaging domain, because we believe it's very important. But here, but frankly speaking, we have more challenges than solutions. So here, we really like to share what we have done and what's the open problem for the fairness and the bias issue in medical domain. So we would, okay. Okay, so we know that deep learning has numerous promise applications in medical imaging analysis. For example, we can do some we can train a deep learning model to some automatic disease diagnosis, for example, to the future breast cancer prediction. Also, deep learning can be used to find the imaging biomarkers. So here, we show a real-world application to find imaging biomarker discovery in the major depressive disorder. Well, it seems like deep learning will be quite useful in medical imaging analysis, but actually, it has not been widely deployed in real-world clinical practice. Why? Because in general, deep learning model is not trustworthy, generally treated as a black box model. So the main barrier into the deployment into clinical practice that we're really lacking a trustworthy model. So what is a trustworthy model? There's no unified definition, or there's no very clear definition. So here I just list some of important components in trustworthy model. For example, a deep learning model should definitely have a transparency and good interpretability. For example, if we just train a classification task use a deep learning model, but still we don't know how it makes decisions, right? So if we can use some prior information to train trainable attention to help us to have a better understanding how we can make such a clinical decision. Also, this phenomenon appears in the segmentation tasks. For example, if we just train an end-to-end segmentation model, it just provides a segmentation map. So if we can inject some uncertainty estimation, it'll be better, it helps us in better understanding, have a more transparent model. So another important aspect in medical domain is that we can always observe the bias and unfair and prediction discriminations. So we all know that in machine learning model, generally we can observe a prediction discrimination towards some specific subgroup of the population. So here we recently biased models have been recently discovered also in medical imaging domain. For example, if we want to train automatic disease diagnosis from your chest X-ray images. So here, a recent paper showing that it has significant bias on sex, age, or races. For example, here, the female patient has significantly high, and the relatively younger patients has significantly higher false positive rate. That means there exists a significant bias in the underdiagnosis rate, because that means, for example, for younger patients, they may have a higher underdiagnosis rate than relatively old patients. Also, your prediction model will be biased if you have different skin color. For example, a recent science paper showing that if your skin color is relatively light and your ROC-AOC curve will be significantly better, then Roche-Hu color will be significantly darker. So all this, like, we just show like two concrete and recent examples showing that in medical imaging, the bias and the prediction discrimination are widely existed. And when we really want to have need to understand the bias and to mitigate the bias. So so here is the overview of the presentation today. So we start talking about some very basics about group fairness. I will talk about some like very, very popular fairness notions. And then we'll focus on our group calibration. And I will talk about some theoretical properties. And most importantly, we'll talk about how, if we use a meta-learning, it can be provably ensure a group calibration, as well as a small generalization error. Well, we also will further talk about some unique challenges in bias mitigation in medical imaging domain, because it's different from machine learning context. So in the bias mitigation in medical imaging is much more challenging, because the first reason is that the distribution shift in medical imaging is much more complex than the standard data or the data in machine learning, such as tabular data or the standard computer vision data. Then the second practical challenge is that in general, we have like multi or missing sensitive attribute in patients. This is, for example, for a specific patient, it may have like your demographic information as well as your clinical information. So in here, if you want to ensure fairness to patients, it's much more a challenge. Also in clinics, there are also sometimes we always have like missing sensitive attributes due to the data collection, due to the issue in the data collection. So all this challenge makes the biasing problem in medical imaging is much more complicated than the biasing in the conventional machine learning. So definitely we have not addressed all these kind of issues. So in the second part of my talk, we just propose a very simple and effective approach to address the second issue. I mean the multi and the missing sensitive attribute. So before starting the talk, talking about fairness, so in this talk we just focus on the group fairness. So let's start talking some like basic notations in group fairness. So in group fairness, we have 4 notations. So the first two random variable is X and Y. So X is input data. It can be your medical imaging, your input feature. Y is the ground truth label. So F is a predictor. So these are all the same with the supervised learning scenario. So the predictor can have some prediction output Y hat. So the key difference in group fairness and between the group fairness and the conventional supervised learning is that in group fairness, we want to ensure some of there's no prediction discrimination with respect to a specific protected feature or sensitive attribute. So what can be looks like for the protected feature? So in general, in machine learning, we need to ensure fairness towards a specific demographic feature, such as age, race, or sex. Also in clinic or in the medical domain, we also need to ensure there's no bias towards your clinical feature. For example, the patient with large tumor set and a small tumor set should be treated equally. You should have no prediction discrimination. So the group fairness is what we just want to ensure a fair predictions for specific subgroup A. So A here can be your demographic feature or your clinical feature in medical context. So a very natural question in fairness community is that, what is a fair prediction? So actually, there's no unified definition. Sure, it really depends on our specific objective and a specific problem and a specific context. what we are talking. So I just list some of common statistical fair notions. Definitely are even much more fairness notions I have not listed. So due to time constraint, definitely I could not explain all this kind of statistical fairness notions. So I just want to discuss some most popular fairness notions in the machine learning community, like the demography and equalized odds. And also I talk about our group calibration. So let's start the first fairness notion, demography. So what is demography? That implies if, for example, if the output of a predictor is independent of your sensitive attribute, that side, the fair prediction satisfies demography. So here I just propose a very simple example to show. So for example, if we have male patients and female patients. So if your output probability is not equal among your male patients and female patients, so here on the criteria of demographic parity is not fair. If your output prediction is equal across male and female patients, so here your predictions fail under the criteria of demographic parity. So the second fairness notion we call it as equalized odds, which has slightly different form with demographic parity. So here we want to ensure the conditional independence. Your prediction should be conditionally independent of your sensitive attribute given your ground truth label Y. So here I still use some like simple illustrative example to show the property of equalized odds in male patients and the female patients. So here in equalized odds, we have like the probability of four probabilities, because here we are conditioned. So suppose it's a binary classification. So here we have like we have four probabilities which are conditioned on male patient and the female patient, and also depends on your ground truth label. Suppose it's binary. So here we have four probabilities. If one of them are not equal, so it's not fair on the criteria of equalized odds. So the prediction is fair on the equalized odds if these four probabilities are equal across male and female patients. So equalized odds, if we take a statistical viewpoint, it ensures your true positive rate and your false positive rate are identical between the different subgroup of demographics. So we all talk about so these two fair notions are quite popular in machine learning literature. If you check the machine learning fairness paper, so we'll talk about some its potential limitations when we're using these fair notions in the medical context. So we all know in the medical context, the disease heterogeneity is quite common. For example, we have different base rate for different subgroup of population. For example, suppose a disease frequency for relatively younger patients is 0.3, and for older patients is 0.6. That implies, if we just treat your age as a sensitive attribute, that implies that your age is not independent with your ground truth label because your base rate is different across these two subgroups. So this will introduce some inherent trade-off in controlling your generalization error or accuracy and fairness if we use these two criteria. So the justification is rather straightforward for demographic parity, because in demographic parity, we just want to ensure your output prediction is independent with your sensitive attribute A. So here, if the sensitive attribute is inherently not independent with your ground truth label A, so intuitively, it's impossible to simultaneously achieve both criteria. So for equalized odds, it has similar kind of potential limitations. For example, we can formally derive some theoretical lower bound to justify there always exists a generalization error and the trade-off between your generalization error and the equalized odd bound. So here it shows that for any kind of predictor or classifier, the sum of your generalization error and the gap of your equalized odds is larger than some constant. So, and this constant depends on the difference between your base rate. So if your base rate is so large, the generalization error plus the equalized gap is larger than some very large constant. And at this moment, if you enforce the equalized odds gap equals to 0, that implies that your generalization error will be very large. This is something theoretically we can justify. There's a lower bound in controlling the generalization error and the equalized odds gap. So we'll talk about the third criteria we call the group calibration, which will be the main focus today. So how about group calibration? So the group calibration is defined as mathematically, later we'll talk about its situations. So here the group calibration is defined as your conditional expectation, your calibration behavior on the overall data set does not change across different subgroup A. So we can theoretically justify that in group calibration, there's no such a trade-off in controlling your fairness metric as well as your generalization error. Even your sensitivity attribute is not independent of your ground truth label. And also, group calibration is very important in healthcare. Indeed, we start analyzing group calibration because we get inspiration from some papers which show that the consequence of group calibration bias. So in a recent paper, it shows like if we train a machine learning system to evaluate the health risk score of different patients. So given a theme, so for example, if a machine learning system will produce a risk score, the same risk score for Black patients and white patients. So indeed, the Black patients are actually considerably higher than white patients in terms of the real disease severity. So if we just translate this text into a mathematical language, it's indeed the group calibration bias. So it's something like your conditional expectation of y given fx equal to tau. The fx equal to tau means that your machine learning system produce a risk score tau. So the actual disease severity on Black patients are significantly higher than white patients. So that this example shows that there is a significant calibration bias in the different demographic subpopulation. So I think some of you may have heard about calibration or prediction calibration because this concept is somehow like quite popular in the Bayesian inference or Bayesian statistics. So here we just have like a very brief discussion and a comparison between these two concepts. So the prediction calibration or calibration itself, it just depends on your prediction confidence is consistent with the ground truth output or your accuracy. Well, here in group calibration, that implies that the calibration property across all the subgroup will be identical. So there's a distribution shift phenomenon. So I will just propose a very simple illustrative example to show here the difference between the calibration and the group calibration. So here, suppose we have two subgroups. Both subgroups are poorly calibrated. So subgroup 1 is overconfident. Subgroup 2 is underconfident. But simultaneously, if we compute the calibration error on the overall data set, it's perfect calibrated. That implies that a small overall calibration error does not imply a small calibration bias. That means, okay, we just train a model and compute its calibration error on the overall data. It does not imply the subgroup level, you still have a good calibration property. It can be something like that. One is overconfident, one is underconfident. Also, this problem will be much more challenging if we have many subgroups and each subgroup just have few data regions. So that means the group calibration is, we talk about group calibration because it has a distribution shift problem and it's much more challenging than calibration. So in our recent news paper, we start understanding some theoretical properties of calibration bias. So the next part, I will talk about something like some theoretical properties in controlling calibration bias and showing how meta learning could effectively control calibration bias. So let's start some theoretical analyze theoretical properties. So in order to measure your calibration bias, we first need to define a metric. So here we call it as calibration gap. So here it's very intuitive. We just compute the calibration on your overall data set and their calibration on your subgroup distribution, and we compute its gap here. And then we take expectation. So in our paper, we show the upper bound to how can we control the calibration bias. So the upper bound is very simple. If we want to control, so that means that if we want to control calibration bias, the calibration bias is controlled by the upper bound between your predictor itself and the subgroup Bayesian predictor. So here we introduce a new and critical concept here is that the conditional expectation of y given xa. So we call it as a Bayesian predictor on the subgroup specific level A. So we know that the Bayesian predictor in general is optimal for specific distribution because it's a ground truth distribution. So here the subgroup Bayesian predictor is optimal for the specific subgroup A. So if we just optimize this upper bound, and we can easily get something like that, if fx is approximately equal to the average over the all subgroup Bayesian predictor, the upper bound will be controlled. So that implies that fx could, if we use the fx as the average of all the subgroup Bayesian predictor, that means that we can simultaneously control the calibration bias and simultaneously the fx is optimal to control the risk. So it seems like we address the calibration bias, right? Because we already have this closed form fx approximated to the average of all subgroup Bayesian predictor. So a very naive solution is that, okay, now we have a data set and we just split the data by its subgroup. For example, suppose now here we have three subgroups. We just split the data by S1, S2, and S3. And then we train three different subgroup predictor, F1, F2, and F3 to approximate its ground truth Bayesian predictor on the specific subgroup. And then we compute its average. It seems it's done, right? And this method is very similar to the ensemble method in machine learning. Well, unfortunately, this does not work quite well in practice because if we just split the whole data by the subgroup data, it can have some like low data regime. For example, in general, the sensitive attribute is not balanced. In some specific subgroup, that might be some very few short data. So if we just use S3, for example, just have 10 samples and we train a model from S3, definitely here, FA is not equal to its ground truth Bayesian predictor because it has an overfitting issue. So what can we do? So if we just take a closer look at the FX itself. So ideally, the FX itself should be informative because it's the average of your worst Bayesian predictor on the specific subgroup. So FX, ideally, the ultimate goal should be informative. So it is possible, like when we want to train F3, it's possible like we just use FX as a prior information to help training F3. So if we can use, because FX itself should be informative. So when we want to train a F3 in no data regime, intuitively, we can just use F as a prior. So here we can construct a meta learning objective by simply treating F as a prior knowledge. So I think most of you have been heard about meta learning. So the high level intuition of meta learning is something like, okay, we have many tasks. And meta learning is that, okay, we want to learn some informative prior from all this kind of tasks. So the maximum shared information, like informative prior, definitely intuitively like, okay, it could eliminate some task specific information because this is the goal of meta learning. We want to learn prior from the many tasks. And in fairness community, a very interesting question is that we know meta learning could somehow mitigate the task specific information. and to learn the shared information. But the interesting theoretical question is that what kind of fairness notion we are ensured? Because we know meta-learning could ensure sort of, but it's still unclear what kind of fairness notion we can ensure. So in our newspaper, we first justify that meta-learning, if we use a meta-learning free objective, we can probably achieve group calibration as well as controlling a small generalization error, definitely on some assumptions. So the objective here is that we have a data set which may have biases. So we want to learn a fair and informative predictor through a meta-learning framework. So here, just a simple reminder of what is meta-learning here. So meta-learning, in general, meta-learning has like a two levels loop of optimization, inner loop and outer loop. So in later 2 slides, I will discuss how the inner loop and outer loop could probably control the calibration bias as well as have a good generalization property. So our ultimate goal is always like learning a fair and informative predictor through meta-learning. So first, we discuss the inner loop in meta-learning. So the inner loop in meta-learning is that we want to learn the subgroup specific predictor F1, F2, F3 through the subgroup data S1, S2, S3, and a prior F. So how can we, so we have, as we discussed before that, we have a low data regime in certain subgroups. So how can we address this problem? So if we have an informative prior, the generalization error bound, because the generalization error can be effectively controlled due to this informative prior. So this can be somehow formally justified through a pack-based theory. So here, so the back-based theory here implies that the generalization error of your different subgroup specific predictor depends on your empirical risk minimization, sure. And also the sample complexity, which depends on the care distance between your informative prior and the subgroup specific prior. So here the intuition is that if my prior is much more informative and useful, the second term can be significantly controlled. So if we just minimize ERM, so the second term cannot be controlled because it can be overfitting. So here we use pack-based theory to justify in the inner loop. Here we can effectively control the low data regime scenario. So in the outer loop, what can we do? So in the outer loop, as our theory suggests, we need to update F being close to all the subgroup levels. So now we have F1, F2, F3 trained on different subgroups. So then we want to update F by being close to all three. So here we can easily use a very simple L1 norm optimization by training F being closing to all this kind of subgroup. So the theoretical motivation of this is that if we just say the upper bound of calibration bias, definitely the F depends on the discrepancy between the different subgroup Bayesian predictor. So here the subgroup Bayesian predictor are trained approximated by F1, F2, and F3. So here we just to control this upper bound by minimize F by controlling its calibration bias. So here the two, yeah.
Thank you. I have a question. So you condition on X. So let's say X is an image, like a medical image. How could you find the same exact image for different subgroups? It wouldn't, you know what I mean? Because I mean, how could you generate like another image that's identical but representing a different group?
I understand your point. So
because maybe the other images for the other groups are not identical, you know.
I see. I understand your point. So here, this is exactly the problem. I understand. So in general, we cannot find the same image. I mean, the same covariant between on the different distribution. So here, actually, we're just doing is optimize its parameter on the model parameter itself, on the output.
Yeah, I mean, theoretically, it's fine. I'm just talking from the point of view of the practical point of view. How am I going to do this in practice?
Here we just are doing a more like the output of your image, because here the fx will be because here if you take a close look at here we're just more interested in the output. For example, you have a model and an image, and your image pass a model and get some output score, right?
Yeah, but the condition on X comma A means that I have the same exact image and I have many forms of it for different subgroups.
Oh, I see.
That wouldn't happen.
Yeah, that would not happen in high dimensional data. Yeah, we just use approximation here to.
Yeah, I'm just like thinking from a practical point of view of
exactly.
how this is going to be applied.
Indeed, we do not really define the same identical X, but we just use the output of a network because that will be one-dimensional and just find them that matched.
Okay.
Yeah, so I totally agree with the point here because we find such a kind of issue important in medical. So indeed, you see here, like we indeed, like in our newest paper, we did not evaluate on the medical data set because it's too challenging to evaluate. So, but in order to like a proof of concept to justify, okay, meta learning somehow like could control your like to improve your generalization error as well as control the calibration bias. We did something like a standard benchmark NLP benchmark data set. So here is the toxic prediction. It just give your text comment and we just predict it's being toxic or not. So here we just compute this average and the calibration bias. And so here is our proposed meta learning framework. So it can achieve a better accuracy and the lower group calibration gap. So if we, and then further we compute the calibration error for each subgroup. So here our proposed method can significantly control the calibration error on some specific subgroup, whereas the standard baselines could not control the variance between the calibration error across different subgroups. So a very natural question is that now we have theories and we justify that it works as a proof concept, it works well on some benchmark data set. The real question is that could this kind of algorithm be really deployed in medical imaging domain? This is a real challenging question. So before answering this question, we should first to know the assumptions in this meta learning framework. What kind of assumptions we really required to ensure such kind of our meta learning works. So in our ICMNUS paper and the recent ICLO paper, that shows that if we want to ensure group calibration as well as a small generalization error by using meta learning framework, first, we should definitely have some assumptions in the data distribution. The first assumption can be there are some distribution similarities between your different Bayesian predictor. So here, the Bayesian predictor only depends on your data set, right? So it's just your data distribution similarity. Well, in general, this assumption is a bit more hard. So we could have some relaxed assumptions. That means it can be possible that we can know existence of representation function that on the embedding space, your Bayesian predictor defined on the embedding space are similar. So to give a more intuitive example to say the feasibility of such a kind of assumptions, I just propose an example on the standard benchmark data. So here is a well-known waterbirds data in algorithmic fairness and biasing community. So the task is we want to predict waterbird and landbird. The challenge is that in most waterbirds have a strong correlation with its background, water background. But you know, the background is not the causal factor of waterbird. So the A is highly correlated to Y, but A is not the cause of Y because we just care about to predict it's waterbird or landbird. We don't care about the land background or water background. So here there's a well-known problem. I think most of you have heard of that. We call it superior correlation. So does meta learning could address this kind of problem? The answer is yes, because if we could learn a representation of bird, that means such a kind of like equation, like the assumption 2 somehow can be approximately achieved. And in that scenario, we could use a meta learning framework to simultaneously achieve small generalization error as well as a small group calibration. But unfortunately, so yes, this is true, this happens. But unfortunately, in medical imaging, the distribution shift is much more complicated than superior correlation or waterbirds dataset. So here, if we just use the waterbird dataset and train a debiasing method, it really works on this kind of real world medical imaging data. So here is the medical imaging data from our lab. So we have like a current base MRI. We want to predict, okay, give such an MRI image. We want to predict, okay, in the future, you have future new lesion activity or not. But the challenge that is here that the sensitive attribute or subgroup is much more complicated than water-based data set. Because here, in real clinical data, we have age, have sex, have its lesion property, like your lesion volume, your lesion location. You see the green marker here. It has numerous, a high-dimensional and a very complex sensitive attribute A. So here, it's very hard to say such assumptions satisfy in our real medical data because there are significant, very complicated distribution shift phenomena. So the distribution shift in medical data is very, very complex. Why we mention this? Because if we completely ignore the theory and the practice gap, there will definitely have some risk recently revealed by some empirical paper. So in a recent empirical paper, I think in IQ this year, they did a numerous empirical study in the bias mitigation in medical imaging benchmark. They show that the state-of-the-art bias mitigation methodologies do not necessarily improve fairness over the empirical risk minimization. So empirical risk minimization just implies that, okay, we just train model without considering any fail constraint. That means sometimes your state-of-the-art debiasing method can be even worse than empirical risk minimization. So here they evaluated numerous many like debiasing state-of-the-art method, and ranking them. So the smaller means better. So here, EIM is here. So if you see, there are many like debiasing method, and the EIM is sometimes it's even better than some state-of-the-art debiasing method. So we think that the problem comes from because such a kind of bias mitigation method generally only consider like water-based data set or some standard benchmark data set. But indeed, in real medical imaging data set, the distribution shift is very, very complex. It's much more complex. So here we really need a better understanding of data distribution shift in real medical data because the sensitive attribute is so complex. Apart from the complex distribution shift, we have a second challenge. So still like here, it's very complicated phenomena. So we have like multi and missing sensitive attributes in medical imaging. So suppose we have one patient, and this patient can have multi-dimensional sensitive attribute. For example, patient A, she has some sex, age, race, and your numerous clinical features like your lesion volume, like your tumor size, something like that. So if we just simply use our previous meta method and the retraining on each sensitive attribute, marginalize on each sensitive attribute, the training procedure will be so long. The second problem is that in real clinical practice, the missing sensitive attribute in patients is so common. For example, in patient B, due to its privacy issue or some concerns, some clinical data collection procedure, for example, maybe the age, race, or lesion volume are completely missing. So here we cannot simply use the imputation method because the imputation could introduce additional bias because you have a distribution shift phenomena and you just simply use imputation is not reliable. So it may introduce additional bias. So here is the second challenge in bias mitigation and medical imaging domain. So we have discussed these two main challenges in medical domain, different from standard machine learning or computer vision community. The distribution shift is complex, and they have multi and missing sensitive attributes. But unfortunately, we have not addressed all these kind of issues because it's a really challenging task. So so in my second part, recently we just aim to address the challenging two as a practical problem. So we know there may exist a multi and missing sensitive attribute in medical imaging data, but if we have but we can propose an alternative solution. That means, is it possible we can mitigate calibration bias if we don't know A during the training procedure? So the motivation is something like that. If we don't know subgroup, your sensitive attribute information during the training procedure, and we can possibly mitigate calibration bias. Here, when you have multi or missing sensitive attribute, it does not matter because the training procedure does not require A. So based on this, our lab recently proposed a very simple and practically very effective method in medical imaging to mitigate the calibration bias without lowering A. So the simple method is just contain two main steps. So the first step, we want to identify some possible samples with maybe possibly poorly calibration. So the method is very simple. Like first, we train identification model, as the vanilla training. Then we compute its individual barrier score on all these kind of samples. And then we use any kind of clustering or something to find the samples with poorly calibrated. The second step, okay, now we have the cluster. And then we can use group-wise focal loss to mitigate the calibration bias. So the focal loss I think some of you have been heard of that. The objective focal loss is we want to penalize some confident predictions by some like exponential term gamma. So the group-wise focal loss is just a way adaptively penalizing the confident prediction to ensure calibration bias. So definitely in medical imaging, there's always a trade-off in controlling calibration bias and optimal prediction because the data distribution is complex. So here, the second step is in the test time evaluation. Now we have like multiple medical images, like we have male, female, and its different lesion properties. And we use our trained model to predict its future MS patients, to predict its future lesion activities. So then we can simply evaluate on different subgroup of a sensitive attribute. For example, we can evaluate them on male or female patients, young or old patients, or patients with a large or small lesion. So here is our result, empirical result. We compare some like recent machine learning baselines, and it shows that it seems like our method could effectively control the calibration bias with a smaller, worse performing calibration error, as well as like a best prediction performance on the worst performing subgroup. If the test sensitive attribute is age. Also, our method works quite well in clinical or clinical-based features. For example, if the feature is your GAD lesion count, and our model like have about 1% performance degradation in prediction performance, but simultaneously we have about like 7% improvement in calibration performance. So here we show like a more intuitive example to show our method could indeed improve calibration bias in real-world medical imaging application. So the left part is the reliability diagram of empirical risk minimization. The left figure is the reliability diagram of our method. So here, like if you say the overall population and the relatively younger patients, the calibration error seems quite similar, right? But if we take a close look at the relatively older patients, we see here in the empirical risk minimization, the calibration error on relatively older patients is significantly different from the relatively younger patients. But well, in our proposed method, the calibration error has been significantly improved. Yeah, sure, it's not a perfect calibration, but compared with empirical risk minimization, the calibration error of the older patients are significantly improved. So here is the summary of our talk presentation today. So we first discuss the group calibration, and the important feature that is relation to meta-learning. And under some specific scenarios, we can guarantee group calibration as well as small generalization error. We'll further discuss the unique challenges in bias mitigation in medical imaging analysis. The two challenges, the complex distribution shift and the multi and missing sensitive attribute. And lastly, we'll propose a very simple and effective approach to address this issue, to address multi and missing sensitive attribute issue. So definitely, during my research this year, I should say, we have more challenges than solutions, because understanding and mitigating bias in healthcare and medical imaging is still very challenging. We have more open problems than solution here. So here, I just propose some like a few simple future ideas, maybe if you are interested. So currently, we are just focusing on the group fairness and the overall performance. We theoretically justify that, okay, if you use meta-learning, if we use meta-learning, we can simultaneously achieve this too. But simultaneously in fairness literature, we still have individual fairness. This is a very important concept in precision medicine because individual fairness implies that we want to make sure everyone is being treated equally. So still currently we don't know the theoretical relations between individual fairness, group fairness, and the overall performance. So if now exists such a trade-off in controlling the three components, it's still open and a challenging question. The answer is we don't know. The second challenge is that our recent middle paper empirically reveals that state-of-the-art bias mitigating approach seems like a trade-off in controlling the fairness in terms of prediction performance as well as uncertainty, which is a very important component in trustworthy machine learning. So we found like it seems like the trade-off in controlling the bias and the fairness mitigation as well as the uncertainty. That means, okay, if we control the bias, have a good bias, if we successfully mitigate the bias in the subgroup, for example, same accuracy, the uncertainty becomes worse for specific subgroup. It seems like it's a trade-off, but still like there are numerous open questions here to explore in the future to have a better understanding the bias and fairness issue and its relation with model uncertainty. The second challenge is that we're still far away from a better understanding of bias because currently we're just focused on the black box fairness notion. We just have a model and compute its output. And okay, we do some statistical tests to say, okay, your prediction is biased. But unfortunately, we really don't know where does the bias come from. So I think a very important future direction might be, we really need to develop some like white box fairness notion. For example, to correctly or to have a better understanding the source of bias. For example, we just have a medical imaging data and it has a poor performance. But and it has a bias prediction, but it's really like we really want to understand if the data has a bias, or your model is wrongly used, or your training procedure is not correct. So these are I believe will be very important aspect in algorithmic fairness in medical domain to have an in-depth understanding the source of bias. So thanks so much for your attention today. I'm talking so many things in fairness and these applications. So I would like to thank so much for my wonderful collaborators, Justin, Raga, Brennan, Tar, Doug, and Christian and Boyu. So and all like other my PVG members, and also thanks my sponsors like to provide the data and the funding for me. Yeah. Thank you.
A bit of time for a question. Are there any in person? We have a question online. In fact, do you want to ask your question directly? If you have a mic, otherwise I'll read it.
Yes,
So Kenfak was asking whether there exists some public data set in the medical domain that can serve as benchmark for bias assessments.
Yes, thanks for your great question. I think we can have like a public data set for bias mitigation. For example, sorry, not here. For example, here, I think the MedFair, it proposed several public benchmark and evaluated different debiasing methodology and and to show, okay, the real data in medical data, what fairness method looks like. Yeah, you can check the website, this benchmark data set. Yeah.
Any other question? Both in person and online. Just waiting to see if there are questions online. Okay, otherwise, if there are no more questions, we're on time. So thanks again, Changjian, for this amazing talk. For everyone, feel free to drop Changjian an email. I put the recording and the slides on the public T-Talk dataset. And I'm sure he'll be more than happy to engage in a more thorough discussion about his work. Thanks again.
Thank you. Should I stop sharing?
Yeah.
Okay.